All right, let's get started. Hi, everyone. My name is Peter Scherbak. I'm a graduate student in astronomy at Caltech. And today I'll be talking about what we can learn from reverse modeling of white dwarf binaries. My collaborator in this work is Jim Fuller, also at Caltech. And the main result of our work is that white dwarf binaries suggest a common envelope efficiency alpha about 1/3. But before getting into the common envelope and convincing you that you should be using this value of alpha, I'll give a recap on existing white dwarf binaries that we know about, focusing on short period double white dwarf binaries, where both components in the system are white dwarfs. In the past decade, there have been two main surveys discovering these sort of systems, first of which is the ELM survey, which is targeting extremely low mass white dwarfs. This has found about 100 double white dwarfs with orbital periods less than 1 day. The second survey is ZTF, which has been mentioned before. Since 2019, ZTF has discovered more than 10 double white dwarfs, all with orbital periods less than 1 hour, 60 minutes, which is quite short. And about half of these are eclipsing. Shown here actually is the light curves of two of these eclipsing double white dwarfs discovered with ZTF at 21 and 24-minute orbital periods. Now, these systems are interesting in a lot of respects. For example, there are going to be LISA verification binaries. But for the purpose of this work, our focus is on reverse modeling these binaries, understanding their evolutionary history, and what we can learn from that evolutionary history. To do this reverse modeling, it's nice to have well-constrained systems where we have information on both components, M1 and M2 in the binary. In practice, that means eclipsing systems are often better for our needs. Specifically, we model 9 double white dwarfs, 7 of which are eclipsing and pretty well constrained. 4 of those eclipsing, including these 2, are from ZTF. And we also model 1 eclipsing white dwarf brown dwarf binary, which has also been modeled in some other works. So in this case, the companion to the white dwarf primary is not another white dwarf, but a brown dwarf. So what do I mean by reverse modeling? The first step in our analysis is to find the birth period of these systems, which is what we call the orbital period when the white dwarf primary is formed. That is very relevant because the white dwarf primary, M1, as the hotter and more luminous white dwarf, is very likely to have formed more recently. It's the younger white dwarf. Our first step in the analysis is simply to estimate the age of M1. So its cooling age, its age since it formed, to as it is observed. We do this by creating a grid of white dwarf models in MESA, concentrating our efforts on a grid of helium white dwarf models because the low mass primaries that we're modeling are more consistent with a helium core. These primaries have observed temperatures and radii, so we fit our white dwarf cooling models to the observed characteristics to estimate the age of M1, the primary. But we want more than the age, we want the orbital evolution of the system since M1 formed. Fortunately, that's pretty simple to do because these systems' orbital evolution is dominated by the emission of gravitational waves, in which case this simple formula for the rate of change of the orbital separation holds true as a function of some of the orbital parameters. We can integrate that equation to obtain this one, where the term on the right-hand side contains this delta t. So this is the elapsed time between the formation of the system when M1 is formed until observed. That's from the cooling age that we just modeled. And on the left-hand side, we have this A final to the fourth minus A initial to the fourth, so the initial and final orbital separations, where the final is from the observed period and the initial is what we want, the birth separation / birth period. So we just use this equation for all 10 systems that we model and find the possible range in birth period, where the black dots are the observed period and the the green bars are the ranges in birth period. Note that for a lot of the long period systems, the range in birth period is pretty small because of those long orbital periods. Gravitational waves aren't that efficient at making the orbit in spiral, so the system must have been born pretty close to the observed. With some of these short period systems, especially these four discovered by ZTF, there are such short orbital periods that there winds up being a decent uncertainty in when the system was born. So we now know the orbital period of the system when the white dwarf primary was formed. To go further back in the evolution of the system, we need to understand how the white dwarf primary formed, and that leads us into the common envelope event, which is necessary for in-spiral to the short orbital periods that we're working with. So there was a very nice talk earlier about the common envelope event, which saved me a little introduction, but focusing on this schematic where that shows some possible evolutionary pathways to creating a final double white dwarf binary, we're going to concentrate on these last few stages, where first of all, we have a giant and one white dwarf in a binary. The giant expands, initiates the common envelope. The core of the giant and the white dwarf in-spiral into a tight orbit, ejecting the envelope and leaving behind a final double white dwarf binary. The important point here is that M1, that this common envelope process leads to the formation of M1, the primary white dwarf, and we just modeled the birth period when M1 formed, so we now know the post-common envelope period for these systems. And that means we can start to investigate the efficiency of the common envelope. I don't need to talk too much about this equation, but some efficiency, alpha CE, of the change in orbital energy from pre to post-common envelope states goes into the unbinding of the envelope. And we just found the post-common envelope state. So now we need to move into the modeling of the pre-common envelope state to obtain both the initial orbital energy and the binding energy of the envelope itself. But from the birth period, we have the final orbital energy. So moving into this pre-common envelope modeling, the first step is to create a mapping between progenitor models and the final white dwarf that these progenitors form. So the progenitor models are stars on the RGB, essentially with helium cores. We make the assumption that the giant with mass M progenitor will initiate mass transfer when its core equals the mass of the final white dwarf, because this progenitor goes on to form the white dwarf primary. And we use that criteria to make this chart, which essentially shows allowed pairings of white dwarf mass and progenitor mass where a common envelope is initiated. I'm going to focus on, should be a green region, I'm not sure what color people see it as, but this region here, where a helium white dwarf is formed from the common envelope event. Note that for a given white dwarf mass, so say we know the final mass of the white dwarf, there's a pretty broad range in potential progenitor mass for most of this space, from about 0.9 to 2.3 solar masses. But for a given configuration, for an example purpose, let's assume 0.35 solar mass final white dwarf. Let's say we want to know the energy budget, assuming a 2 solar mass progenitor, shown by this arrow here. We can determine the pre-common envelope period and therefore get the orbital energy as follows. We want to investigate a 2 solar mass model when its core equals 0.35 solar masses. And from the pre-common envelope criteria, when that model's radius, that model will initiate mass transfer when its radius equals its rho slope, when the radius of the giant equals the giant's rho slope. Then we can use this equation relating the rho slope to the orbital separation depending on the mass ratio Q, to finally relate the radius of the star to the orbital separation. The term that's even more important is the binding energy. So same sort of deal for a given model. We can integrate over the envelope from core mass to total mass for both gravitational and internal energies, where the integrals are shown here. Staying on the topic of this binding energy, it will depend both on core mass and the total mass of the progenitor. The binding energy plotted here will increase with decreasing core mass because that means the progenitor is less evolved on the RGB and more compact. The binding energy will increase with increasing progenitor mass just because there's more mass in the envelope. So for a progenitor mass range of 0.9 to 2.0 solar masses, there's this inherent uncertainty in the binding energy. Even if we know the core mass, there's this range in binding energy that just depends on the mass of the progenitor. We can now put these ingredients together to estimate alpha CE for all systems. This is the same equation I wrote earlier, but now with terms subbed in for the orbital energies. Note the specific term I'm assuming for the initial orbital energy, which is a little in contrast with the previous talk. But essentially, we have the binding energy of the progenitor, we have the initial orbital energy from the rho slope overflow criteria of the progenitor, and we have the final orbital energy from the birth period of M1, the modeling I talked about at the start of this talk. And for each possible configuration, we can generate a value of alpha CE for these 10 systems. And the ranges in alpha CE, so between minimum and maximum values, are shown here. Minimum values tend to be around 0.1 to 0.2. Maximum values can vary a bit. Some are even above 1. Note that here I am assuming a progenitor from 0.9 to 2.0 solar masses. Relaxing that a bit turns out not to matter that much because the parameter space of possible progenitors above 2.0 solar masses that parameter space from those progenitors tends to be pretty small. However, there is this uncertainty in progenitor that winds up manifesting in an uncertainty in binding energy, which of course leads to uncertainty in alpha CE. If I assume that a single value of alpha CE should be involved in the creation of all 10 systems, all 10 binaries, then an alpha CE of about 0.2 to 0.4 works best. I sort of fitted for the value of 1/3, just using these error bars, these ranges. And I will conclude by admitting that I sort of lied at the start of the talk when I said, I'll convince you that there's one value of alpha CE. Even with this analysis, there is a range, obviously. But I do believe that our work, in conjunction with a lot of previous work mentioned in Monica's talk, does point to low common envelope efficiencies alpha, replicating a lot of systems. I will end there, and happy to take any questions.
Questions? Oh.
Hi, this is Warren Brown. Nice analysis. I'm just curious how sensitive you are to the age of the white dwarf, because they're very likely tidally heating up right now. They're not cooling off.
Yeah, so we only model systems at orbital periods larger than 20 minutes, longer than 20 minutes, and we think that'll avoid the strongest tidal heating. So a lot of gyms work on that tidal heating really kicks in at periods under 20 minutes. So we think we've probably avoided most of that. But that is a complication, you're right.
Yeah, I was just curious if you plan to extend your work to include higher mass progenitors. just because, I mean, in the context of double white dwarf mergers, which the sample is, the sample of double white dwarfs, of course, is not as large. The ones that would plausibly make type 1As, they stem from initial masses on the ZAMs on the order of 4, 5, 6 solar masses.
4, 5, 6. Yeah, that's a bit larger than we've gone. We did go up to 2.8 solar masses, where we think it's less likely that those masses lead to these systems. But we did try that. Yeah, I'd be curious for the 4, 5, 6 what values of alpha CE we get. I'm sort of afraid that we're going to get pretty large values, but I'd like to check that.
Fair enough. Cool.
Hey, Peter. Thanks for the great talk. I was wondering about the assumption you mentioned about how mass transfer starts when the core of the progenitor equals the mass of the companion.
The mass of the primary white dwarf, sure.
Yeah. Yeah, so I was just wondering what motivates that.
Yeah, sure. So the one thing I could say is that the time scale for the core to grow up to RGB is going to be a lot longer than the time scale of the common envelope, which will be around 1,000 years. So it's pretty likely that the core is not going to grow a lot during the common envelope. We did one thing we checked is differing definitions of core mass and how that affected the binding energy, and that turns out to be a secondary effect. So I don't know if that completely answers your question, but
yeah, thanks.
Yeah, I'm wondering because these are double white dwarfs, and I always have problem with the double white dwarfs and trying to reconstruct them because, okay, you assume the common envelope phase was producing the currently hotter white dwarf, but you don't know what happened before. If it was another common envelope, which I don't think it's very plausible, but if it was stable mass transfer, then the progenitor of the current hotter white dwarf, so the common envelope, it's from a star that got mass. So the envelope might be slightly different because then you have more hydrogen. So this might affect, how do you calculate the binding energy, for example? You use single star models, I think.
Exactly. We use single star models in MESA. Yeah, that is something we thought about. And one caveat that might help is the binding energy, the contribution to the binding energy is greatest near the core. So a little bit of mass on top from a companion might not matter too much. But you are right. Even in this diagram, there's two pathways for this first episode of mass transfer, common envelope and something stable, I guess. I think recent work has pointed to stable mass transfer, but that's just not an assumption we're making. Correct, yes.
So I appreciated how you ended your talk with the point that maybe, there's not some universal value, alpha isn't a law of physics, it's a parameterization of our ignorance, right? Would you maybe recommend, if we could constrain a range, maybe putting in sort of like random draws from a range of 0.2 to 0.4 in a binary population synthesis model rather than just like one value? Or I don't know. Yeah. What are your thoughts on that?
Yeah. I would have to think about that a bit more with binary pops in, but probably random draws. One thing that me and Jim have thought about, and this goes back to the question about tidal heating, is trying to extend this to systems with where you think there will be tidal heating, and then sort of choosing a value of alpha and seeing if that replicates these systems with some tidal heating. And even in that analysis, I'm thinking not to do just a single value of alpha, do a range of 0.2 to 0.4 probably. But yeah, so I don't know if that completely answers your question, but I would say do a range.
Thanks, yeah.
Okay, thank you very much.
Thank you.
And thank all the speakers.